Thanks. Yeah, so let's get into it. So this joint work with Scott Aronson and Luke Schaefer. So sort of in case you sort of stumbled into the quantum query complexity section sort of accidentally, just wanted to start with a brief overview of what query complexity is. So if you have a language and you want to determine membership in that language, you could sort of measure the complexity of an algorithm in several ways, such as time, space, and what have you. For query complexity, we only measure the number of input bits that you access during the computation. So how many bits do you need to access in order to actually determine membership of the word? So for deterministic algorithms, this is quite straightforward. So imagine we have the language of OR. So this is just like all words such that one of the bits is set to 1. And consider this sort of 4-bit word here. Initially, I don't know what it is, so I might query some bit. And if it's a 1, then that's great, right? Because then I don't need to look at any of the other bits. I already know that this word must be in the language, so I can just output, yes, I'm in the language. Otherwise, if it's 0, then like I don't know yet. Maybe there's a 1, maybe there's not, so I have to keep searching. So then I might query the fourth bit. If it's a 1, then great, I know it's in the language. Otherwise, I don't know, and so on and so forth. So in general, the deterministic complexity is just, you take the best algorithm and you take the worst input for that algorithm. So clearly for a deterministic algorithm on OR, you're sort of stuck, right? You must look at all the bits because you could just keep getting zeros until you finally see the 1, right? And this intuition, so this is the deterministic complexity of OR, is just n, right? And this intuition also holds for randomized algorithms as well, because you might just keep sampling various points, but if they're all zeros except for one of them, roughly it'll take n over 2 queries to actually hit that 1 to know if it's in the language. So for quantum algorithms, it's a bit less straightforward, right? Because it's unclear like which bits I'm actually accessing. So we measure the quantum query complexity as the number of calls to an indexing function. So an indexing function just takes an index I as input and it sort of XORs the corresponding bit into another register. And then it's just the quantum query complexity is just the number of calls that you have to this indexing oracle such that you can determine membership with bounded error. So something slightly non-standard that I want to go ahead and point out right now is that in general for this talk, our alphabets won't be binary. They'll be finite, but they won't be binary. So in this sort of step right here, you could just think of this as sort of just encoding the input in some sort of binary encoding, and that'll work just fine as well. Okay, and so sort of famously, the quantum query complexity of the OR function is square root n instead of n. So we get some savings there. But for there are functions such as parity, such that you still need to look at all the bits. Okay, so now that we sort of know what query complexity is, why study query complexity? For one, it's sort of provable lower bounds. That's great. It's really hard to get those. And on the other hand, like these lower bounds aren't totally useless. A lot of times you can actually prove the lower bound before you can prove the corresponding upper bound. And so the lower bounds can actually point you to some very nice algorithms, and that's sort of what's going to happen in this talk. So what about regular languages? So what is a regular language? There's many, many ways to define a regular language. I'll choose to define them through regular expressions. So there's some basic sets which are sort of just a priori going to be regular languages. So the empty set is a regular language. The set containing the empty string is a regular language. And sets containing a single letter from your alphabet are also going to be regular languages. And then we sort of can combine them together in the following ways. So we can, the concatenation of two regular languages is a regular language, the union, and the Kleene star. If you haven't seen this Kleene star operation before, it's just 0 or more concatenations of elements in your set. So we'll see some examples here. So imagine we have the alphabet 0, 1, 2. First of all, we can construct the alphabet itself. We can just take the set containing 0, union the set containing 1, union the set containing 2. And this will just be equal to the alphabet. A bit of notation here, these braces are often like kind of cumbersome, so we often drop them. So we can just say like 0, union 1, union 2, and that means the same thing. Okay, if we apply the Kleene star operation to this, and that just gives us all of the possible words that we could generate from our alphabet. Of course, you can do more complicated things as well. You can express the OR function, so you can see as many zeros as you want, but at some point you need to see a 1 for that to be in the language, and then you can see whatever else you want. Slightly more complicated is this AND-OR function. So this is why we introduced this 2 here. So we have 2's in our language, which sort of delimit the ORs. So between every pair of 2's, you must have a 1. And so this is why it sort of corresponds to an AND of ORs, because all of the ORs must have a 1. And then finally, parity is also a regular expression, a regular language, the language that has an even number of ones in it. Okay. So why do we care about regular languages? Well, they're really, really nice, right? They're closed under, most operations you can think of. Like we already know that they're closed under concatenation, union, and cleany star just from the definition of regular expressions. They're closed under complement. They're closed under reversal. Many, many things that they're closed under. Also, like many natural questions that you could ask about the language are decidable. For instance, you can ask, given a regular language, is the language infinite, right? Like this would sort of be hopeless if you were given a Turing machine, but if you're given, a regular expression, this is easy. And finally, they have extremely robust definitions, so you can define them in many different ways. I already sort of gave you the definition in terms of regular expressions, but another thing that you may have seen is the definition in terms of finite state automata. If you haven't seen this before, but you do know what a Turing machine is, it's like a Turing machine, but you don't have any read-write tape. So you can just sort of read the input once, and then you're done. And then finally, they also have some very nice algebraic definitions as well. So they're recognized by finite monoids, and we'll actually sort of see this later in the talk. Okay, so if we think about quantum query complexity and regular languages, then it's sort of we're taking this sort of regime in which we can actually prove things, and we're taking these regular languages, which are these very, very nice set of languages. So hopefully we should be able to say quite a lot about these languages. So we just sort of start enumerating languages. Let's just see what happens and look at their quantum query complexity. Okay, maybe the empty set, that's not too interesting. That has constant query complexity. Maybe slightly more interesting is the language that begins and ends with 1. Okay, that's still not so interesting. All right, the OR language, from Grover's algorithm has a square root n algorithm. And even AND-OR will also have the square root n algorithm. Okay, I lied to you slightly. We actually don't know how to get square root n. We only know how to get square root n with some log factors. We'll get into that more later. And then finally, languages like parity have quantum query complexity, which is omega n. Okay, so this is not an accident how I've arranged these buckets here, or the title of the talk, in fact. So this is the theorem, right? So the trichotomy theorem is that every regular language has quantum query complexity either constant, square root n, or n. Okay, so there's some very nice sort of consequences from this. In fact, so not only do we know what the quantum query complexities are, we actually have exact characterizations of the regular expressions or regular languages which correspond to each one of those complexities. You'll see that in a second. And then finally, all of the upper bounds in this trichotomy theorem come from explicit quantum algorithms. So we actually get the corresponding quantum speedup if you were actually trying to run this algorithm in practice instead of just the query bound as well. Okay, so what are these classes of regular expressions? So the ones that have constant query complexity are not that interesting. They're just regular expressions that depend only on constantly many symbols at the beginning and end of your string. The second class of star-free are called star-free languages. These are very interesting, and we'll get into it more later. But a priori, they're just regular expressions where you take out the cleany star, hence the name star-free, and you add the complement operation. And then finally, regular languages are just general regular expressions that don't fall into either star-free or trivial. And just as a reminder, this is actually sort of a hierarchy, right? The regular languages contain the star-free languages, and the star-free languages contain the trivial languages. The only inclusion here, which is sort of not straightforward, is maybe the regular languages contain the star-free languages, but regular languages are closed under complement, so they have all of the power that star-free does, and they also have cleany star. So before I go into sort of talking about the proof, there's one sort of major caveat here. I've lied to you yet again. So consider the following language. It's parity, but only on even length strings. And so this language is sort of manifestly regular, and yet if we look at its quantum query complexity, something strange happens, right? So on words of odd length, there's nothing to do, right? We know they're not in the language, so we don't have to query anything, just immediately return that they're not in the language, right? But on strings of even length, then all of a sudden we have to solve the parity problem. So the query complexity is sort of going to oscillate drastically between 0 and n, right? And so sort of technically speaking, the query complexity of this language is neither constant nor n, right? So how do we fix this? There are several ways. One way is just to sort of redefine what the standard notion of query complexity is, right? Instead of saying the query complexity is the complexity of strings of length exactly n, you say the query complexity is of strings up to length n. And this will sort of smooth everything out. And then if you have this redefined in this way, then like you recover the trichotomy theorem exactly. If you're not happy with this redefinition, then you can just sort of take the caveat as just part of the theorem, like that you might have this oscillation. Okay. So I mentioned earlier that the AND-OR language, right, had this square root n algorithm, and yet we know that the square root n algorithms must be characterized by star-free expressions. And yet when I sort of wrote AND-OR earlier, it's sort of filled with stars, right? So sort of, by the theorem, it must be the case that AND-OR can be written without stars. And indeed it can. There it is. Exercise to the reader. It's actually not too hard, but yeah. So there are many ways of characterizing star-free languages. They've been studied since like the 60s. One of the nicest characterizations, I think, is this following characterization by McNaughton, which says that a language is star-free if and only if it is expressible in first-order logic with the less than relation. Okay, so that might be sort of a mouthful, but once you see some examples, I think it'll be kind of straightforward. So for instance, the OR, right, this is star-free, and we can write it as there exists some index I such that there's some bit xi which is equal to 1, right? Or AND-OR, which is also star-free, we can write as for all indices I and j that are equal to 2, that are sort of separated apart, there exists some index k in between them such that k is 1. Right, so this is also star-free because of this expression. And what McNaughton's theorem says is that, well, we can have any number of alternating quantifiers that we want here, right? We can extend this to any constant number of quantifiers, and that'll still be star-free, which is great, right? Because this is sort of like a very nice generalization of Grover's algorithm, right? Grover's algorithm, you typically think of just like, exists some index such that some nice thing happens. And now we can sort of have these alternating quantifiers instead. So it sort of extends the quadratic speedup to like a much larger class of sort of string processing algorithms. So one potential application of this is sort of the direct generalization of the AND-OR language. So you can solve sort of in square root n time these sort of dynamic constant depth Boolean formulas. So what do I mean by the word dynamic? I mean that the format of the formula sort of changes from the input. Normally when you think of Boolean formulas, you think of the formula sort of fixed in advance, and then you sort of change the variables. But in fact, even the structure, you don't even know the structure of the problem until you sort of look at the input itself. Okay, so sort of the outline for the remainder of this talk then is just going to be a brief sort of structural overview of the proof, and then sort of dive into the sort of most interesting part, which is the square root n algorithm for star-free algorithms. Languages, thank you. So as I said earlier, the upper bounds all come from explicit algorithms, right? So for the trivial languages as well, this is sort of obvious, right? They only depend on the constantly many symbols at the beginning and end of your word. So there's just a constant lookup table, so you have a constant time algorithm. That's not interesting. Star-free algorithms, or star-free languages are more challenging. More on this later. And then finally, just if you have a generic regular language, well, you can always solve it in linear time just sort of by appealing to the machine definition of a regular language, right? You just sort of read one bit one at a time, and then when you're done reading, you sort of don't have any workspace left, so you must sort of just answer. Okay, so that's sort of just a brief overview of those. On the other hand, we need lower bounds as well, right? And so we need to prove that if your language is not trivial, then your quantum query complexity is omega square root n. And we need to prove that if your language is not star-free, then your quantum query complexity is necessarily omega n. And I won't get into these proofs. They're sort of subtle and nice in their own ways, but they use sort of standard sort of tools from query complexity, so sensitivity and block sensitivity in particular. Okay, so now let's sort of talk about the square root n algorithm for star-free languages. And let's start with just sort of the AND-OR language that we saw before. And so the idea, right, is just to remind you, right, the AND-OR languages, we have these 2's, and between every 2 pairs of 2's, we must have a 1, right? So to solve the problem then, we might think, okay, let's just search for some violation. So let's search for a pair of 2's such that everything in between them is zeros. Okay, and so like what do you do when you have to search? Well, you use Grover search, right? So here's your string, you look for a 0, and then you just sort of like walk outwards until you find a 2 on each side. And then if you find such a thing, then you reject. Otherwise, you accept. Okay, but of course, if you analyze the runtime of this algorithm, right, you have square root n Grover iterations, which is good, but then your work per iteration, if you're just taking one step at a time, is n. So then you just have this abysmal time at the end. So that's no good. Okay, but clearly I didn't use Grover enough, right? So let's just put Grover in Grover. So instead, let's sort of search for a 0 again, but now let's sort of increase our window a little bit each time, and each time we're going to Grover for a 2. So we keep searching until we get a 2, and sort of binary search for a 2 in this way. And when we do this, we're still going to have square root n outer Grover iterations, but our inner work is now sort of reduced to the length of the match, right? So if this match up here has length L, then we only take square root L time, right? But still, like my whole string could just be 2, 0, star 2, right? So L in this case could be n, in which case my total time is still n, right? So I still haven't done anything that great. And so what's really the problem here, right? The problem is that this outer Grover, it takes square root n, is sort of taking all my time already, right? But now we can just sort of appeal to a very nice fact about Grover's algorithm, is that it's faster when you have multiple marked items, right? So we're searching for a 0 in between two 2s, right? But if the match is length L, right, then there's L many zeros that we can possibly hit, right? So the intuition is that when there are t marked items, the Grover search is only going to require square root n over t iterations. So then the full strategy is now the following. You sort of take an exponential search over the length of the possible match that you might find, right? You Grover search for an index in the middle of that 2, 0, star 2 string, and then you sort of Grover and binary search outwards to find a 2 on each side at a distance of most L. And that completes the algorithm. And the analysis is the following, right? So the outer Grover takes square root n over L, the inner Grover takes square root L, and therefore altogether you take square root n time. And sort of I keep hiding in these tildes here a bunch of amplification, right? So just know that there's some amplification needed to make this work. Okay, so if you look at this algorithm, so what made it work, right? And I want to claim it's the following, that when we searched for an index 0, we sort of split our language in half. We were looking for 2, 0, star 2, but when we looked for a 0, we sort of split it in half and say on one half we're looking for 2, 0, star, and then the other half we're looking for 0, star 2, right? So we can sort of generalize this notion of splitting a language. So instead of looking at the language 2, 0, star 2, let's just look at a generic star-free language. We say that a language splits in the following way as a union over these AI and BI if this union is constant. And for all words that are in the language and for all decompositions, you're either going to be on one half of the split or the other half of the split, just like you would be in this 2, 0, star 2 case. So as an example, like this 2, 0, star 2 splits as this union here. And these two cases on the end are just sort of, they're not interesting, but sort of completeness, they're there. So we can sort of use this idea of splitting to sort of generalize this AND-OR algorithm. So in the AND-OR algorithm, we're searching for a substring 2, 0, star 2. And now let's imagine we're searching for a substring that just matches some arbitrary language. So we're searching for some substring that matches the language L in the string. So we're searching for something of the form sigma star L sigma star. And we have this theorem now that says that if the language splits like this, and we have algorithms for all of the split languages, then we can combine those algorithms to get an algorithm for the substring search, which we call infix search. So what's the proof? Well, the proof is exactly the same, right? So you search for an index, and on either side, now we know that you have to be an AI on one side and BI on the other side. So you just search. And since there's only constantly many AI and BI, you can just sort of iterate over all of them, and you're fine. So the proof is exactly the same. So now that I've sort of introduced this sort of more general way of doing this infix search, where is this going, right? So we're trying to find a square root n algorithm for all star-free languages. So we need some sort of way of sort of decomposing a star-free language into some infix search problems. And the way we do it is exactly like this. So there's this beautiful theorem by Schützenberger, which I'm going to state very informally now and then maybe get slightly more formal later, but not too formal. Which says that given any star-free language, there's like a hierarchy of component star-free languages. And any language in that hierarchy can be expressed as languages lower down in that hierarchy via this Boolean combination here, right? So if you were able to, if these languages are star-free, then clearly the language above is going to be star-free as well. And then, of course, notice, sort of most importantly, that we have this infix search algorithm here, which we now know how to solve. But, OK, there's a catch, right? Just because this language A3 is at a lower level in the hierarchy doesn't mean that when you split it, all of the component languages will also be at a lower level in the hierarchy, right? But actually, a remarkable fact is that this does, in fact, occur, right? A3 is going to split into simpler languages, which means that this gives us a very kind of clear plan, right? We're going to take a language, we're going to split it into these component languages, and if we can find square root n algorithms for all the component languages, we can sort of piece them together in this way to get a language, to get a square root n algorithm for the whole language. Okay, so something that's very much not obvious and that I won't get into is that if I have a language, if I have an algorithm for A1, a square root n algorithm for A1, I don't actually need the algorithm for A1, right? I need the sort of the suffix algorithm. I need the algorithm for sigma star A1. This is, in fact, is not obvious, but this is OK. If we have a square root n algorithm for A1, then we can solve the corresponding prefix and suffix problems as well. And this will also hold for all of the split languages of A3. This has to do more with the structure of A1 and A2 and A3, which I won't get into. But I do want to give you some sort of a flavor of what goes behind this proof. And it's going to involve this algebraic characterization of regular languages that I mentioned earlier. So it requires a bit of a definition here. So a language L is recognized by some monoid, M, if there exists a homomorphism from the set of words to this monoid and a subset S of the monoid, such that your language is equal to all of the words that your homomorphism maps to that set S. Okay, that's sort of a mouthful and maybe hard to internalize at first. In case you don't remember, a monoid is just a semigroup, so there are no inverses, but it does have an identity element. So as an example, let's just sort of look at the monoid for OR. It's just this two-element monoid, right? In which the homomorphism just maps 0 to 0 and 1 to 1. And if any of your bits of your input is going to be 1, then that monoid product is also going to be 1, which means you're going to land inside the set S, which means you'll accept. So this is just a small example. And then sort of the beautiful theorem by Schützenberger is that a language is star-free if and only if it is recognized by a finite aperiodic monoid. Okay, so this should not at all be obvious. Aperiodic means that for all elements in your monoid, there's some n such that m to the n is equal to m to the n plus 1. That's not important for us. So how does this proof work and how does it help us? Well, the direction that we'll need is the direction which starts with a finite aperiodic monoid and builds a star-free language out of it. And basically, what Schützenberger does is he takes sort of some simpler elements in the monoid and builds star-free languages out of those. And then he combines them in this way to get to get other monoid elements. So this is the briefest proof sketch I could think of, right? So once again, we just have the same decomposition. So once again, we can use the infix search here, and we can use the prefix and suffix search here, and that's going to complete the algorithm. So we basically follow his algorithm step by step, except in each case, he wants to build a star-free language, and we want to build an actual algorithm. OK, so that's all I'm going to say about the star-free algorithm. I wanted to spend, in the last few minutes here, I wanted to spend a brief moment talking about context-free languages. So regular languages, right, have this very regular structure to them, right, which sort of forces their query complexity to be, one of 3 buckets, right? But so you might ask, okay, what is the defining property of regular languages that makes it so? Maybe even larger classes, models of computation have the same sort of thing. Well, the context-free languages, if you haven't seen them before, they're much like the regular languages, except your finite state automata is sort of equipped with this stack. And they're slightly more powerful, but they're still restricted in several ways. And yet, sort of the trichotomy is sort of obliterated by the context-free languages. For every algebraic number between 1/2 and 1, we can find a context-free language L such that the quantum query complexity of L is exactly n to the c. In fact, if you're willing to sort of relax your notion of quantum query complexity sum and you're willing to be sort of O of n to the c plus epsilon and big omega of n to the c minus epsilon, then you can get all limit computable c in between 1/2 and 1. If you haven't seen limit computable before, it's sort of a generalization of computable. And in fact, we even have a converse. So if L is context-free, then the quantum query complexity of L, if it's n to the c, then c must be limit computable. So that's all I'm going to say about the context-free languages, but it clearly breaks the trichotomy. So what are the open questions here? Well, one of the main open questions is whether or not you can remove all of these log factors. I didn't mention it so much when I was talking about the proof, but at each step in the recursion, we're going to incur more log factors, right? So the monoid is going to be finite, which means there's only finitely many levels of recursion, so that's okay. But it's a big constant for interesting languages. So can we remove these log factors? Even removing the log factors from the AND-OR language would be very interesting. Secondly, can we complete the classification for context-free languages? We have it between 1/2 and 1. Are there any interesting problems that have query complexity strictly between 0 and 1/2, end of the 0 and end of the 1/2? I sort of conjecture that this is not the case, but I'm also not able to prove it. And then finally, are there sort of applications of the star-free algorithm that we sort of haven't thought of? Okay, thanks.
Questions? Yes?
So have you tried using like span program kinds of ideas for this first question? It seems like a really natural thing to try to do.
Yes. Well, so Shalev and Ben David has thought about this and is able to shave off, I think, like a square root log factor from the AND-OR algorithm, but not able to shave off all of the log factors.
Okay. Thanks.
Yes?
Sorry, about quantum finite automata? Yeah. Not that I know of, but I also haven't thought about it, so maybe.
Okay, yes.
Do you have any kind of like characterization about, given a context-free language, well, how do you find out what its exponent is? Can you characterize the property that makes the exponent large or small or anything?
I mean, to answer exactly, no. But like for instance, like the context-free languages are sort of a strict superset of the regular languages. So sort of you can port the regular languages over. The reason that you get this sort of n to the c for all sort of limit computable exponents is because with context-free languages you can sort of verify that a computation history is correct. And so this gives you a way of sort of simulating an arbitrary Turing machine, which is how you get that. So I don't know if that's an answer, but that's sort of an approach.
Other questions? We still have some time. Yes.
I was just curious, how did you have the intuition that the regular languages will have this trichotomy?
Well, yeah, so it's actually, sort of amusingly, like, yeah, we just started trying them out. And, you just eventually realize that, like, you can't find anything else. And in particular, we had this AND-OR language very early on, and we didn't know how to solve it. We thought it might be n, we thought it might be square root n, we didn't know. And then when it turned out to be square root n, it was like, well, okay, maybe they're all just this. And then we proved the lower bound, and then it was like, okay, this has to work.
Okay. Yeah.
So I was just confused at the beginning when you said odd string length strings don't have any query complexity for a parity function, but how do you know how long a string is without making some queries to it?
Okay, so I did sort of brush over this. In the query complexity model, you always know the length of the string.
Okay, cool.
Yeah, I mean, if you didn't know the length of the string, you would sort of, you wouldn't like, your first decision might be to query the like 100th index, but that, that index might not even exist. So you sort of need to know what what the size of the input is.
Okay, yes.
So, a lot of the work on generalizing Grover's algorithm and doing quantum searches have looked at things like two-dimensional grids of symbols and stuff like that. Now, that's not going to be my question, because as soon as you get it to a two-dimensional grid, this hierarchy where you have simpler languages like regular gets wrecked pretty quickly, so that it becomes Turing complete with cellular automata or stuff of that sort. However, what I was wondering about is, suppose you had a function from a tree to a finite set of symbols instead of from the integers to a finite set of symbols. You could have a class of languages that way, and I don't even know, but I'm wondering if there is a version of CFLs for tree-shaped strings instead of linear strings, and then whether you could expect a version of these results.
Maybe the short answer is I don't know. I mean, yeah, that's a good question. I don't know.
Okay, so I think it's time now. So thank you again.